So to continue our discussion of matrices, we're going to be looking at a couple other operations we can do on matrices in these next couple videos. We talked about adding, subtracting, and multiplying. So now we'll talk about, I'll say division, but I'm going to kind of put it in quotes. I'll talk more about why it's not really division. We'll get back to that. And we're also going to talk about the determinant in these videos. So just a couple other operations we can do on matrices. All right. So to begin with, let's just talk real quick about division. And I'm going to go back to sort of our regular numbers. And I'm actually going to use all the operations, not just divisions. But let's just say, okay, I have, I don't know, 2 plus 2. We all know that that's 4. And then 2 minus 2 is 0. Now, technically, this second part, we all know this probably, but oftentimes we don't really recognize it. This is the same as 2 plus negative 2 would equal 0. So really, we can kind of think of subtraction is really just adding a negative. So really, you can almost say there is no such thing as subtraction. Although there is, obviously, there is subtraction. We use it. It makes things a lot easier. But we could also think of subtraction as just adding by a negative. Similarly, with multiplication, if I do, I don't know, something, let's just stick with the 2. If I do 2 times 2, I get 4. If I do 2 divided by 2, I get 1. But really, I could do the same thing as I did above. I could just say, well, this is just 2 times 1/2, and that'll give me 1. So in this case, we could say, well, there's actually no such thing as division. We would just multiply by 1/2. Now, obviously, we have division. It makes problems easier to do. But in terms of the framework of math and what mathematicians needed to do was sort of generalize these concepts so that we're not just dealing with numbers. So they really, what basically happened is they said adding and subtracting are the same thing. There's really no distinction between them. And the same with multiplying and dividing are the same operation. And what folks decided was, well, we have to define a couple of key words. So in this case, we're going to call something the additive inverse. Additive inverse. And so this means that if I am given some a, its additive inverse is just negative a, because a plus negative a equals 0. So for example, the additive inverse of 2 would be negative 2, and we just saw that 2 plus negative 2 is 0. And we also need something called an identity, so the additive identity. The additive identity is 0. So basically, if I took any number a plus 0, I would always get a. And so that's how they define it. They defined what's called the identity element, and in this case it would be additive. With multiplying and dividing, again, these are the exact same thing. Multiplication and division. We again have it's called multiplicative identity. And in this case, so if I have a, its multiplicative identity is a to the power of negative 1. This is really 1 over a, but to keep things kind of simpler, they use a to the negative 1. And this is because if I took a times a to the negative 1, it equals the multiplicative identity, which is 1. Sorry, I think I multiplicative inverse. Sorry, I actually misspoke here. This should be multiplicative inverse, not identity. Oops. So the multiplicative inverse is a to the power of negative 1. And then the multiplicative identity is 1 because a times 1 equals a for all a in the real numbers. Now this is true, so multiplication division only works, all this stuff only works if we're not including the additive identity, because 1 over 0 doesn't really make sense. So 0 is the only number that does not fall into this category. Okay, so this is kind of, obviously I don't want you to just get rid of division and subtraction. Those still exist, we still use them. But as you progress further in sort of theoretical math fields, we end up thinking about these sets as multiplicative inverse and identity. It just helps later on. And we'll see an example of that when it comes to matrices. So let's go ahead now and let's come back to matrices for a moment. With matrices, division really doesn't make sense. So if I took, I don't know, like, let's say 2, 1, 5, 3, and I divided this by 6, negative 1, 3, 8, or something like that. This just doesn't make sense. We can't really divide matrices. There's no formula for this like we had with multiplication. So what mathematicians said is let's actually define a couple of quantities. So for matrices now, we're going to define let me start with additive. So we're going to define the additive inverse. Now this works out the same way. I'll come back to multiplication and division. But if I have a, well then I can just subtract a. That works out okay. And identity element is something called the zero matrix, which is just a matrix with a bunch of zeros. It sort of depends on the problem because, again, it depends on dimension. So sometimes we just write 0 or even just 0 for that. The point of the zero matrix is it's just however many zeros you need. If the dimension of A is a 2 by 3, then the zero matrix is a 2 by 3 matrix. It really doesn't matter. More importantly, in this chapter, in this section, we're going to be talking about multiplication. And mathematicians first had to figure out, well, what is the identity element? They said, how would we define an identity here? And they said, well, it's some matrix. Let's just call it I for identity. It's some matrix such that if I took any matrix A and I multiplied it by the identity, I should end up with A again. So they said, what matrix works for this? And it was actually found that the matrix with ones all along its diagonal, so if these are all ones, and then everything else is a 0. So this is a matrix ones on diagonal, zeros everywhere else. And what they also found was that this has to be a square matrix. So what I usually do is I call this I with a little n next to it. And so this represents the n by n matrix, or sorry, the n by n identity matrix. For example, if I wanted the 3 by 3 identity matrix, I would say, well, that's going to be the matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1. I2 would be the same thing, except it would just be 1, 0, 0, 1. So these are probably the two most common ones that we'll be using. Anytime you get to 4 by 4s or bigger, it just turns into a long, tedious, complicated problem that we don't really want to deal with. So we're going to stick with I2 and I3 just to kind of get the basics down for matrices. And so what they discovered was this equation I wrote here, that actually holds true for all A. If we multiply it by the corresponding identity matrix, then we end up with the same matrix back again. Now, the next piece of this, now that we have the identity element, the next question was, well, what does it mean to have the inverse? Again, we're talking about multiplication. And mathematicians said, well, we know that in multiplication, if I take some number and I multiply it by a to the power of negative 1, I should get 1. And so they just sort of adjusted this to represent matrices, and they said, well, let's just assume that there's some matrix such that this equation is true. And so then the question that we'll be answering today is, what is this and how do we find it? But the point of this entire discussion so far, we really haven't done any problem solving yet. I haven't given you any equations to solve, anything like that. But the point of this whole discussion is to just kind of show that based on what we know about multiplication from numbers, this can be extended to other sets of things. In this case, my things are matrices. So now we're going to be extending this idea of inverse to matrices, and we're going to talk about what that means.